Hello, this is Desmond Parker with A Plus College Ready. Today we will be talking about drawing molecules. There's a wide variety of ways that we will see these molecules drawn as you continue out your chemistry career. One of the ways that we will see these is what we call a structural formula. Typically, you will see a lot of these in organic chemistry, and it basically shows us what the molecule would look like on a two-dimensional surface and how these molecules are bonded together and the location of the bonding. Hopefully by now you've covered Lewis dot structures, so I'm just going to do a quick recap. You have paired electrons and you have unpaired electrons. If we take a look at this chlorine molecule, so we have three sets of molecules that are paired and we have one that's by itself. Now looking at carbon, this is what we call excited state carbon, which is typically what form carbon is in. Ground state carbon's electrons do not look like this. But in excited state carbon, we have all unpaired electrons. So just in case you've forgotten about your noble gas notation or electron dot notation, typically we're going to have four sides of the molecule, each representing a different type of orbital. These first two electrons should go in paired, and then we're going to put one at a time in. So you would go 3, 4, 5, and then you go back in pair, 6, 7, 8. And this is following Hund's rule. So make sure you do not break Hund's rule when drawing Lewis dot structures of just atoms by themselves. So when we're drawing the compounds, which that's what a vast majority of your drawing will be, this does not take into consideration the three-dimensional structure of our molecules. So as you are drawing these, and your teacher I'm pretty sure will give you practice using modeling kits so that you can actually see the 3D structure of these different molecules. So we're going to focus only on the two-dimensional structures today, and we'll talk in the next set of videos about the three-dimensional structure of the molecules. So there are several steps to this. The first step is that we need to add up the total number of valence electrons found in the entire compound. So here we have carbon, hydrogen, and oxygen. We have, and this is formaldehyde. So we have 2 hydrogens, so we have to make sure that we take both of those into account. So the total number of electrons that we get will be 12 electrons. Then our next step is that we're going to draw the skeleton of the compound, connecting everything with single bonds. Your atom, which is your least electronegative, and the way that the formulas are typically written, now I'm going to tell you that is not in 100% of cases, that the atom to the furthest left is typically your least electronegative atom. Now there are certain exceptions to this. For instance, if hydrogen was your first atom, hydrogen cannot be a central atom because it does only have an s orbital, and having simply an s orbital does not allow it to form more than one bond. So typically hydrogen does not serve as a central atom. It is perfectly happy being what we call a peripheral atom. So now that we've drawn the skeleton structure of our molecule, as you can see over here on this side, we need to subtract the total number of bonds that we have formed. So we have formed 3 bonds, and each bond counts as 2 electrons. So I have currently spent 6 electrons out of my electron bank account, and I have 6 left over. So the next thing that we're going to do is whatever remaining electrons that we have will go to our peripheral or our outside atoms. The only exception to this is that hydrogen does not get any more electrons. As we've talked about before, hydrogen is happy with just 2 electrons. So I'm going to give my peripheral atom, which is oxygen, the remaining 6 electrons. So those peripheral atoms should get 6 additional electrons, which we gave to oxygen. So we have no electrons remaining. So now any remaining electrons that we have will go on the central atom, even if it does violate the octet rule. So in this case right here, since we have no electrons left over, we have no additional electrons to put on the central atom. Now, if we have atoms which don't have their octets, then we will form double and triple bonds. Now, there are only certain atoms that are willing to form a double or triple bond. So we have carbon, nitrogen, oxygen, sulfur, and phosphorus. Those are typically the only atoms that will form a multiple bond. So if we're running into a situation where we're getting somebody who doesn't have an octet and we don't have one of those nearby, we've probably done something wrong. So what I'm going to do is I'm going to take a set of electrons from oxygen and I'm going to put it in the middle and form a double bond between the carbon and the oxygen. Remember, only form double bonds if necessary. If you can rearrange some electrons around to give octets to everybody, do that first. So we don't want to form double bonds if we don't have to. But in this case, we do. So now everybody's happy. Hydrogen has its 2. And then oxygen has all 8. So it has all of its 8 come from the bond. So there are 4 bonds that carbon is currently has. 1 bond with each hydrogen, a double bond with oxygen. That's a total of 8. Then your oxygen is happy because it has its 2 lone pairs of electrons, which are these guys right here. And then it has this bond here in the middle, which gives it 8 electrons. So you will see some notations and you will see varying notations of how these things are drawn. So sometimes some people like to draw the dots instead of the lines. I prefer, well, you really should get in the habit of doing both. You should be able to show that those 2 electrons are forming a bond together, so draw the lines. That's what I recommend, but again, it depends upon whatever your teacher wants you to do. That's what you should do. And that's our notation for single bonds. Now, if we have a double or triple bond, so for instance, this is a triple bond with nitrogen. We talked earlier that nitrogen loves to form triple bonds. That's how it's going to get its octet, and you will notice that as you count from both of these slides that these molecules all have their octets. Hydrogen has its 2 electrons, the oxygen has its 8, the nitrogen has its 8, and the carbon has its 8, and then on this side nitrogen has its 8. So they're all happy. They want to get that octet, and that's how they're going to do it. So this right here is how we would show a double bond. Again, instead of drawing all those dots on the paper, we can draw it in as 2 lines indicating that we have a double bond being formed. Now we also have what are called resonance structures, and what resonance structures are basically the same atom or the same compound, but we have a choice of where those double bonds can go without upsetting the atom too much. So in this case right here, which is O3, you have the option to put the double bond here, or you can put the double bond here. Either way you put it, it's correct. Now on your AP test, if they ask you to draw a molecule out, and it is a resonance structure, you must show all resonance structures. One thing that's important, another thing that's important about resonance structures is you cannot move the atoms. The atoms have to stay in the same location. So O3 is one of those examples that might be a little bit harder to see, but if we had, let's say that central oxygen was a sulfur, and the peripheral atoms were something else. That would have to, the both structures would have to be the same. The only change you can make are the bonds and the electrons. And both atoms have to have 8. So you will see in this one right here, this has 8 electrons. On this side, on this molecule, we now have again 8 electrons, but we had to put 2 over here, which we took from that side over there. So you have to make sure your electron counts are correct, and you have to make sure that your atoms are not being moved. This is just a list of polyatomic ions. You need to take these and you need to carve them on your soles if you have them, so that you will know these. These are common. They come up on a regular basis. Know what they are. So when we're drawing Lewis structures for polyatomic ions, it's the same process as what we did before. The only difference, 2 differences. One is that we change the number of electrons. So this ammonium ion here has a 1+ charge. So since it has a 1+ charge, that means that it lost 1 electron. So that means that my total electron count needs to be 1 less than what it would typically be. So let me make that make sense. So nitrogen has 5 electrons that it donates. Each hydrogen has 1. So that's a total of 9 electrons. Since this has a +1 charge to it, that means that now I have 8 electrons in my system. So that's the first change. The second change is that it must go in brackets. If it's not drawn in brackets with the charge on the outside, then your answer will be wrong. So let's take a look at an AP level question. So at room temperature, iodine is a molecular solid which of the following provides characteristics of I2 with a correct explanation. Alright, so there are some things in here that you might not know, but there are definitely some things in here that you do know. And so we can go ahead and eliminate some of the things that we that we do know. So this question is question 18, which might be a little bit more challenging because it's starting to get in the middle of the test. The first one that I would probably eliminate would be letter D. We've already talked about polar molecules, and I2 is nonpolar because it has no polar bonds, and since they're both 2 iodines bonded together, it cannot be polar. So regardless of whether or not you knew it was soluble, I would hope that you would know that that molecule was not polar. So I would cross off D immediately. It's not a good conductor of electricity because its valence electrons are localized in bonding and non-bonding pairs. So we do know that because iodine is a nonmetal, that it should not conduct electricity. So that is true. We should hopefully also know that valence electrons are localized because this is not a metal. Remember, metals have delocalized electrons because they are able to go anywhere and everywhere, and nonmetals, they stay with their atom. So I would hope that you would be able to recognize that C would probably be the right answer. B, it is hard because it forms a 3-dimensional covalent network. So again, there are only really 2 covalent network solids that you need to know, diamonds and silicon dioxide. So you could eliminate this one. And you really don't know much about intermolecular forces at this point, but you will later on this unit. So I could see you being stuck between A and C. So A is not correct because it actually has a relatively strong set of intermolecular forces, hence why it is in fact a solid. So I hope this was a helpful video. If you have any additional questions, again, remember to forward them to your instructor, and I will see you all next time.